Today, I'd like to talk about quantum transfer learning for Wi-Fi sensing. I'm Toshiaki Koike-Akino from Mitsubishi Electric Research Laboratory, MERL. First, I want to talk about the trends of machine learning, then show what is quantum machine learning to apply Wi-Fi sensing for indoor monitoring, and summarize the talk. First, I want to talk about emerging technologies. This chart is a Gartner hype cycle released last year. AI is the most important technique, which has a highest expectation in society. Generative AI is also fascinating for many applications. And quantum machine learning, QML, appeared in this chart last year as an emerging technologies, which I want to talk about. AI technologies include a lot of technique, including classical machine learning, like support vector machine. Since about a decade ago, deep learning became most popular technique for AI. And in future, we expect the QML will play the most important role. It is said that Hinton's paper in 2006 was a key turning point to promote deep learning as a key enabler for AI, and the growth was supported by two evolutions, one for hardware and also software. The maturity of hardware side, like GPU, could make us to use high-performance deep learning methods. At the same time, software library hugely supported the advancement. As you know, there are many deep learning architectures, including multi-layer perceptron, convolutional neural network, LSTM, transformer network, UNet, and implicit layers. It showed a tremendous success in medial signal processing for audio and visual denoising, segmentation, classification, and so on. Then, AI even surpassed human-level performance for some specific topics, like gaming. Then, not surprisingly, AI has been also used for wireless communications, as you know. And then I discovered an interesting trend by counting the number of articles in Google Scholar in the last 2 decades for the keywords pair of wireless communication plus machine learning or deep learning. The trends follows the Moore's law, exponentially growing, roughly doubling every year. And now we already have more than 10,000 papers a year. Will this growth continue forever? Probably not. One reason is known as an escalating power consumption requirement for DNN training. This paper is very interesting to show the crisis of deep learning. For one example, to train a very large deep network with network architecture search framework required more than 5 times higher carbon emissions of a single car lifetime. This may be one of extreme cases. However, the community is now seeking a possibility to use a different computing modality alternative to CPU, GPU, TPU type approach. For example, natural computing, including quantum and DNA computing. This talk focuses on quantum computing. Some people say quantum computing can induce the 4th industrial revolution, and the government funds are escalating. More importantly, the maturity of quantum software and hardware is rapidly advancing. For example, IBM, Google, Microsoft, Honeywell, and other vendors are able to produce quantum processors. And you can use the QPU in the cloud, like IBM QX. And also the software side, many free libraries appeared to utilize the power of quantum computing. Last year, IBM announced over 100 qubits QPU, and they plan to release over 1,000 qubits processors next year. Besides superconducting QPU, there are many hardware realizations, including trapped ion, neutral atoms, boson sampling, and so on. Even some people already show a quantum supremacy using superconducting QPU or photonic circuits. But it is still argued that a real quantum advantage exists for a general applications. There are two types of QML framework addressing classical bit or quantum bit. In 2014, some pioneer works appeared known VQE or QA. Those techniques could resolve quantum noise inherently in a noisy intermediate scale quantum processor, NISQ. Then later on, a number of different variational quantum algorithms appeared. NISQ algorithm is different from traditional quantum algorithm like Shor's and Glover's algorithm, which assumes an ideal quantum circuit. In 2016, IBM released Quantum Cloud Server. Then many state-of-the-art machine learning techniques were translated into quantum domain. For example, quantum autoencoder, quantum support vector machine, quantum GAN, quantum convolutional neural network, quantum graph neural network. In the past few years, important theoretical framework was also derived. For example, this paper shows that quantum processor can work as a kernel mapping, like kernel support vector machine. And another important theorems regarding universal approximation property, UAP. It is very well known that neural network can approximate nearly any arbitrary functions by using infinitely large neurons or infinitely large layers. And 3 years ago, this paper proved that quantum processors also hold UAP by using a data re-uploading trick. And then they showed that a sequence of quantum gates operations corresponds to the neuron nodes in classical neural network. And more quantum bits entangled together corresponds to multiple layers in the conventional neural network. This theorem supports that quantum machine can be used as a neural network. More importantly, another paper showed that quantum computing is differentiable, known as parameter shift rule, which is very similar to finite difference, but generating an exact gradient. Because of this rule, we can combine conventional layers and quantum layer in a computation pipeline to optimize jointly through backpropagation. One such example is known convolutional neural network, using quantum circuit to convolve the image data integrated with conventional convolutional neural network that can improve the performance. And how to design quantum circuits? There are many templates called ansatz. For example, layered gates, alternating gates, or TensorNet. For wireless communications, it is envisioned that QML will be a major driver for the 6G applications. Some expectations include few parameters can support exponentially large states in parallel. Then parallel ensembling may prevent overfitting and underfitting. And then quantum processor may be lower power consumption than conventional processor. And when I count the number of articles in the last decade, I found trend agrees on the Moore's law, doubling each year. And this growth rate is same as deep neural network trends. And most interestingly, QML follows just 6 years behind. This may imply that after 6 years, the same society using QML for almost everything in the research community. Okay, going back to the main topic we propose in this talk, we investigate the power of QML for Wi-Fi sensing. In the past, deep learning were used for Wi-Fi sensing, for example, indoor localizations and human monitoring. And today, we show human pulse sensing using commercial Wi-Fi access point, but we assume APA has an ability to access quantum processor, like on the cloud on IBM. We use a spatially rich feature available in Wi-Fi standard, which scans a beam of multiple sectors. And we set up the experimental platform to sense human pose. What we propose is using quantum neural network, using a non-simplified two design ansatz. We use quantum processor, which implements staggered Y rotations with multiple layers with controlled Z gates. The two design ansatz has a good statistical property identical to ensemble random unitary operations. Roughly speaking, any arbitrary unitary matrix of the size of 2 to the n can be approximated by just 2n variational parameters. So we may achieve a quantum advantage of exponential order. This quantum neural network takes a beam SNR features as an input. Then after scaling, the feature is embedded in Y rotation gates. Then after entangular layers, we take measurements. The measured data are scaled again to calculate a pose score. And then the cross entropy loss is minimized by a stochastic gradient to tune the angle of Y rotations, known as variational parameter. We consider only 18 variational parameters to train. Let's see the performance of our QNN. We measure the beam SNR Wi-Fi feature over different sessions, 1 and 2. We consider the first session as a source domain, then the second session for a target domain. We use the source data to train the model, then apply the model to a target domain as a cross-section validation. This figure shows the test accuracy over the number of training samples for various ML methods, including k-nearest neighbor, support vector machine, and deep neural network. And QNN shows a comparable performance of the state-of-the-art DNN for most cases. More importantly, QNN uses only 18 parameters, but DNN uses 35,000 parameters. And this performance can be improved if we just first split the data sets in source domain, in training and testing. Then we use the trained model to the testing data set of the same source domain. So we could see the performance improvement, of course. Here we can see QNN can be best for within session performance, even approaching 100% accuracy. This implies that there is a huge domain shift issue, source domain and target domain. In order to solve these domain shift issues, we propose to use transfer learning framework. Now we have pre-trained model from the data in source domain, and pre-trained model will be refined by using a portion of target domain. We could see that quantum transfer learning can perform comparable to DNN and approaching nearly 100% accuracy. Let's see the result of confusion matrix here for SVM, DNN, QNN, and transfer learning. We see a huge confusion for the pose number 4 or pose number 6. Using DNN or QNN, we can resolve the number 6. However, still the pose 4 is confusing. Then, using quantum transfer learning, we can solve this confusion, leading to a good performance in accuracy and also AUC score of 0.99. Okay, let's conclude the talk. We first showed the recent trends of AI, then introduced the recent advancement of QML. And we applied the QML transfer learning for sensing applications. Specifically, we demonstrated the first proof of concept study for future quantum-ready society. Then experimented using the commercial off-the-shelf Wi-Fi systems to monitor the human indoor. We could show the significant gain to deal with a measurement domain shift by transfer learning. Our QNN achieves the state-of-the-art DNN performance with very few number of parameters and approaching nearly 100% accuracy for pose estimation. We believe our framework has high potential and interesting future work. please contact me for any comments and questions.